The next speaker is Chris Thompson, and he's as soon as I introduce him, oh yeah, you need the plug-in. He's going to be telling us about some of the work he's done on DiaGrid to use Pegasus and other things for remote computation. So, welcome, Chris.
Hi, my name is Chris Thompson. I work for Purdue in the Rosen Center of Advanced Computing in the Scientific Solutions Group. We run a hub named DiaGrid, and we created several tools that I'll talk about today that you've heard from Karen about how Pegasus and some of the back-end stuff works to enable remote computing. And so I'm going to talk from the other side as a tool developer, how we make use of those features. So I'll mention why we compute remotely. I'll talk about a couple of our tools, and then review what we've learned. So there's some users out there who are savvy. They know how to use terminals. They know how to use Xterm and SSH, and maybe they can even write batch scripts. But there's a lot of users out there whose their experience is quite a bit different. They run on just machines they have sitting around in their lab. Maybe they're under a desk, under a bench, and they're slow, they're confusing. Maybe they have to figure out the mechanics of how to actually run some of these executables. They have to, maybe they've figured out a way to script some of their workflow things, but maybe they're just running them manually each time. And so the DiaGrid hub was created with the purpose of having sort of a low barrier to bringing in a lot of people into making use of compute cycles that normally would go idle on campus and in some of our partner institutions. It started as a front end for a Condor pool that's composed of 50,000 cores split up among these institutions that are located in clusters, lab machines. I think there's even some that belong to like desktop office machines after hours were pulled from. Since then, DiaGrid has expanded the DiaGrid hub has expanded to support job types from a lot of different destinations beyond just that initial Condor pool. DiaGrid supports remote computing for a lot of reasons. Primarily which is a lot of programs need scalability beyond just what a user can run locally or what can run inside just the execution host of a hub. Modelers are always wanting to have access to greater resolution for their data sets, more granularity with their time steps, more complexity to their algorithms. And I'm sure everybody's heard the big data buzzword just about everywhere. And those two things aren't mutually exclusive either. As you have more computation, you create bigger data. As you have bigger data, you need more computation to chug through it. We also have a class of users who come into DiaGrid who bring their own access to resources, to computing resources wherever they may be, such as exceed projects where the users will be granted an allocation of a certain number of computation hours on a certain resource, and that's where their stuff needs to run. They need somewhere to host their tool and bring their users to on the web, but that's where their execution has to happen. So we look at this user's new workflow online in remote computing instead of locally. We can see that the hub gives us a lot of great tools, such as the tool sessions and the submit command, where we can replace some of these blocks in the workflow and really upgrade some of the other ones. Instead of just pulling together their data locally, they upload it to one space. They don't have to worry about where it's being staged at. The tool will take care of that, putting it in the right spot for them. They set their parameters. We can design tools so they don't have to try to remember what settings they used yesterday. They can be able to see, we can save them for them. They don't have to worry about where their code is running. They don't care. They just know that it runs. When they click go, submit takes over and runs it for them. And at the end, they're not left with just a bunch of data in a directory. They have options. They can download it. They can share it. They can use all the hub features to publish, maybe go on to use it again, analyze it, or. So the first tool that I'll talk about of ours is Submitter. It, as the name suggests, is for submitting R scripts. It's a simple GUI that runs in the hub tool sessions. It submits to the HPC clusters at Purdue the scripts that users upload and want to run. Allows them to build up a list of arguments that they're in the GUI that their script needs. They can monitor the job as it's running, and it's written in Python. R, if you're not aware, is a language that was first created mainly to do statistics type analysis, but since then it's really gained a lot of popularity, and it's seeing a lot of use in other domains. So the basic user workflow is they'll write their script, they'll upload their script, configure the settings for it, and then submit it, watch it run, and then download their output. There's several different types of jobs that it can support. It can do traditional serial jobs. This is what most people coming in are going to probably have scripts just simple scripts that run a calculation they need to run. But then if users move up to running parallel code, they can do so using the R Snow library. The tool will pick that up and allow them to run on multiple cores and nodes depending on how many cores they request. They can also do parameter sweep jobs where they just define some arguments for their script and then list the ranges here in the UI. And when they click submit, when they click go, submit will create all the relevant jobs based off of those, sweeping through those parameters. So there's the kind of a high-level architecture of where it fits into everything. Submitter runs inside a tool session inside DiaGrid. The user is connecting to it through the web browser, as I'm sure you guys are aware. You know how hubs work. But when the user, with the actual job runs from submitter through submit to the HPC resources. Here you can see on the configuration window for submitter how the user is able to see the options they've selected for their job. So as they enter their arguments and pick the settings, they can see what it would look like as an actual R command that they are running on their command line. And that's a breakdown of where each of those pieces comes from. So they'd select what version of R they want, and then what mode of R they're running. This particular example, they've specified a queue option, which you can see is in there. They specified some parameters to sweep across, and then there's their input file. So that's the command they'd be familiar with on the command line if they were running it on their own machine. But they didn't have to know that, or they didn't have to input that. That came from just being built up from whatever options they selected in the UI. Now, when the command is actually running on the clusters, you can see here's the actual submit command that was sent. The first portion is just the call to submit itself. Debug flag turns on various output options that we can read. The next section is a section that pertains to the location of where the job was sent. It was sent to the Hansen cluster with a wall time of 60 minutes before it gets kicked off, and it's requesting one node. That was put in automatically by submitter. The user didn't have to know those details about the job. Next is a section that is generated by the program from scanning through the list of all the files in their directory. So so the system knows what to send with the job over to Hansen. And then finally at the end there you can see is the actual command the user wanted to run. So that's a bit smaller than I thought it'd be. When in the code itself, the actual process for in Python for calling submit isn't too complicated. So you would create a thread that runs the function, and the function is what does the actual call to submit. So the first step is to build up that argument list for submit. Then it sends a message to the UI to update it to tell the user what's about to happen. Set up some data structures to hold information about the job as it's running so we can collect the output to show them. And then in Python, you use subprocess.popen to fork off and create another process that would run the submit command as if it were just a shell command. Capture up the standard output and the standard error and loop over it, reading it into the UI so the user can see what's happening while it's running. And then when it's done, that standard out stream will close, and you can return out of there. If there's any errors, you want to try to capture those so you can process those. If anything goes wrong while it's running, and then at the end we just update the UI to show the user that it's done. Another tool that we have is Blaster. So what is Blaster? Well, first, what is BLAST? It's a bioinformatics tool. It's fairly industry standard. It's used in sort of wide variety of fields in bioinformatics for searching through large gene databases for gene sequences that match, and to a lot of configurability for determining what matches versus doesn't match. It's a suite of several command line tools that are developed by NCBI. Blaster is a Java-based GUI that runs in the DiaGrid hub that calls BLAST for the user. It manages multiple search histories, allows them to conduct multiple searches at the same time. It handles all the different standard variants of BLAST, and it also maintains an up-to-date copy of the NCBI databases, which a lot of people search against, or allows them to upload their own custom databases. It has a similar workflow to Submitter. The user uploads their input file, or optionally also their custom database. They search through, or they select the parameters they want that'll search through the gene database. They submit their job, they watch it run, and then at the end they can look at their output and download it. And in fact, most of the tools we create follow this same general workflow of upload input, configure, run, download output. So Blaster first started with submitting Pegasus jobs. It was the first mode that Blaster supported. When we first set it up, the databases, we were able to search through the databases in only a few minutes in parallel by breaking up the input sequences. Each input sequence in the input file is an independent search through the database. So a lot of users will have input files that have thousands of sequences. So we can easily break them up into smaller pieces, submit each one as its own job. It's very easy to parallelize. At the time when we started, the databases weren't too large, so they made good sense for Condor jobs that could quickly run in a few minutes of idle time on a spare CPU. However, over time, the databases, new genes are sequenced. These databases continue to grow over a couple of years. They've grown, some of them have grown a couple magnitudes in size. What used to be a couple of gigabytes is now over 100. What used to run in a few minutes now runs in several hours. So it doesn't really make much sense to run them on those quick, small Condor jobs anymore. And so we've been transitioning Blaster over to running on PBS submission to the to the clusters, where we can have longer run times with defined wall times before we get kicked off the nodes. But the HUBZero, the submit system, allowed this change with a fairly small amount of work on our side as a tool developer. Most of the details of this were hidden inside the submit system. We just needed to change some arguments, change a little bit of output parsing, and tweak a few things. But for the most part, it works the same as before, which was a big, really nice feature of using submit. So internally, it's a little more complex than submitter was. There are GUI classes that draw the window, all the different pieces of it. There's a data manager class that holds the history of all the searches users have done in the past, also the ones they're doing currently. And then there is an engine manager for holding all of what we call engines, which are the classes that correspond to each type of search, each type of job in the system. But they all work in the same similar manner. The user interacts with the GUI, which pushes and pulls data through the data manager and uses the appropriate engine to trigger the particular commands and submit for a particular job type, which then goes through submit and off to the various HPC resource that for that type of job. So when the user uses BLAST, when they set up a new search, they're given a bunch of options in the GUI, and they can pick which particular BLAST executable they want to run. They can upload their input file, or they can select an input file they already have uploaded on the hub. They can go through all the different options for the particular executable that they've selected, and there's quite a few of those, and they change depending on which executable they picked. When the user clicks submit, all those options they've picked are bundled up into a job object, which is sent off to that engine manager, which then routes it to the correct engine code for that particular job type. There's a whole bunch of error checking stuff that goes on depending on what options they picked and branches through all of the different possibilities. But when it comes time to run the submit command, we create a thread that we create and start a thread for handling that. Thread will parse through the parameters, set up job data such as moving things to the right location, actually start the submit command, then start a monitoring thread that'll watch and update the UI to the progress of that, and wait for that submit to finish before merging the results from all the different pieces back into one and preparing it for download, like zipping it up and putting it in a place where the user can see it. For monitoring the job that's going on, it's pretty straightforward. We just loop until the submit command is finished, scan for the job status using some of the files that Karen mentioned. There was the Pegasus job stats was one of them. We update the various data structures in the program and then trigger the UI to update the user as to what's going on so they can monitor the status of the job. So inside the submit thread, when we actually want to call submit, we do this by creating a process. Well, first we build up all the arguments that we want to send to submit into an array, create a process, and capture the output streams from it. Then we start up that monitoring thread and wait for it to finish. We don't call submit directly on Blaster. We actually call a shell script which calls submit. And so, but inside here you can see this simplified version of it. You can see the different the different pieces of the submit command that we use. Very similar to the submitter. One of the different options here is submit has a lot of features for allowing you to automatically build up lists of jobs to create, and you can see here we use one here called SCQ. All of the input files for Blaster start with SCQ after they've been processed and split into pieces, and so this parameter here allows us to, without having to specify directly, let submit find all of those pieces and submit one job for each one of them. And so we found that through all the tools we've created for through the HUBZero system on DiaGrid, there's a general format for most all of them. You build up your list of arguments from various places, such as what the user selected in the UI, what you've been able to scan from the job files, or just fixed values like the queue names of the resources you're submitting to, or paths in the system to various executables. Once you have your list of arguments, you have your submit command. You spin off a process or a thread to actually run that, and then wait for it to finish. And while it's running, you monitor the status of that so you can keep the user updated and react to any problems that pop up. And at the end, collect all the data and everything back from it, process it, do any sort of analysis you need to do after the fact. We have several tools on DiaGrid that all do this type of remote computing for users. CryoEM is an electron microscope tool, image analysis tool written in Python and C++. It submits to Condor and PBS. GrowMaximum is a tool that is a GUI for a popular molecular dynamics program. It's written in Java. It submits to one of the local clusters. So there's a lot of different options that are available, but from the tool developer standpoint, they're all the same. They're just submit commands with slightly different arguments. So this wouldn't be possible without the HUBZero team, with the tools they provided through Submit, and the support we get from them is really invaluable. As far as we bug them quite a bit with issues and problems, and they're always there to figure it out. So that's all I have. Any questions?